Good afternoon. Welcome to Global Compliance Panel Team's live webinar on water system biofilm control and microbial monitoring myths. My name is Sam and I'm going to be your host today. On behalf of the Global Compliance Panel team, I would like to thank you for being part of this event. Today's webinar will be presented by Terry C. Solly. Terry C. Solly has a PhD and is a microbiologist and president of Solly Pharma Solutions, Inc. And since becoming a full-time consultant, he has served consumer products and FDA-regulated industries with training and troubleshooting expertise covering water systems, sterilization, aseptic processing, microbiological and beta-lactam contamination control, microbiological laboratory operations, and has served as a pharmaceutical expert witness in several contamination litigations. Prior to full-time consulting, he has served 24 years of diverse big pharma operating company. During his 31-plus-year career, he has lectured extensively at conferences, authored numerous papers, and recently written several book chapters related to water system microbiology for USP, PDE, and ISPE publications. He is currently serving in his third 5-year term on USP expert committees responsible for pharmaceutical waters, through which he authored the complete rewrite of USP Chapter 1231, which many consider to be USP's pharmaceutical water Bible. We are honored to have such a distinguished person such as Dr. Solly with us to present the webinar today. Before we begin, I would like to inform you of the program outline for this training session. This webinar is for 90 minutes duration. First, Terry will take you through today's webinar, highlighting the areas that will be covered, and he would then share with you his presentation. We would like to inform you that all participants, once part of the teleconference, have been placed on mute and will remain so until the Q&A window begins. It is for the purpose of avoiding discontinuity and for allowing the presenter to speak clearly so that everyone present can take maximum benefit from this webinar. We also request all to hold back your questions until the Q&A window begins. 10 minutes of time will be allotted for the Q&A, during which your questions will be answered. If for any reason you get logged out of this training session or teleconference, please follow the same procedure to join it again. Now that we are all ready to start, I request Terry C. Solly to take it from here. Terry?
Sam, are you there?
Oh, yes. Terry? Please continue the session. Are you able to hear me, Terry?
I can't hear Sam. That we create to explain things that happen that we don't understand, that are beyond our control. And this is the way that the ancient history explained a lot of things. You know, they didn't understand the workings of the earth and the solar system and the seasons and birth and death, and they didn't understand all these things, and so they made up these myths to explain what was going on that seemed to make sense at the time. And so in actuality, these myths are continued to be fabricated to this very day. And we're going to be talking about some myths that are associated with water systems, specifically those associated with biofilm control, and a few that are associated with microbial monitoring. So, without any further ado, let's get into a little bit. First, Sam mentioned some things about my experience and my, let's call it, credentials. And I wanted to emphasize the fact that I have been a volunteer and working with USP for a lot of years. But in spite of that activity with USP, I am not speaking for them today. I'm actually an unpaid volunteer when I work with USP. And so I'm speaking as a private citizen, and so the opinions that you hear are my own. They are not USP's. However, because I have been involved in the writing of a lot of things that now appear in USP, you may find some consistency between some of the things that are written in USP and some of my opinions. Nevertheless, I am not specifically representing USP today. So let's get into what we're going to talk about. We're going to first talk about why water myths develop in the first place. And we're going to talk about CGMPs and some the impact of precedences and traditions, and the fact that in our industry we are very hungry to have rules to operate by. And then we're going to get into a few of the microbial control myths that exist relative to water systems. And there's the list of them right there. We'll go in detail into them later. And then we're going to go into a few of the testing myths that exist. And those are the list of those testing myths that we have. So let's jump right into this. Let's get into the origins of water myths. Now, it all really starts off because of the way FDA regulates our industry. They regulate. I say he. They regulate our industry by CGMPs, and we're talking the little c CGMPs, not the big C GMPs. The big C GMPs are the actual 21 CFR 210 and 211 regulations. The little c GMPs are what FDA interprets as the current expected practice. And part of the reason that this evolved was that and it was not the original intent, by the way. There was the original intent that the laws would be changed as technologies were developed and better manufacturing practices were able to be used. But they didn't realize that it literally takes an act of Congress to pass laws like this. And so once the original CGMPs were promulgated, there was no way that the law promulgation process could keep up with the manufacturing and technology developments. And so in order to keep pace, FDA began enforcing based upon their interpretation of what was currently available and currently capable technological practices. So not by specific promulgated law, but by their interpretation of the law. So the question comes up, is this really legal? I'm not going to get into that, but I'm just throwing the question out there. Can they regulate based upon their interpretation, which could change from time to time of what's actually written into the law? And so what we do know is those expectations are tightening all the time. And the question is, do you happen to know today's rules? Maybe they're not the same as yesterday's rules. Now, industry has two responses to breaking those rules. First, if you happen to be a drug innovator and you got a lot riding on the line relative to future approvals of new drug applications and this kind of stuff, and then the potential loss by the delay of those approvals, there is a very strong aversion to even the issuance of any 483 observations by FDA, let alone warning letters. And so there's a very conservative view taken by the drug innovators on compliance. And they are towing the line for the most part. Now, if you look at the generics and the OTC industry, generally speaking, they're not nearly as phased by 483s and warning letters. And there's a reason for that. One of the reasons is that FDA tends to be pretty slow in taking regulatory action in situations where the public risk is low. They've got limited resources, and they're really going to go after the big fish first. They're going to go after the more serious problems first to make sure that the public safety is not in jeopardy. And so any kind of compliance problem in the generics and the OTC industry that is not going to directly translate into immediate public health impact is probably going to be a little bit slower in terms of when FDA can get around to dealing with that. And so what happens in this is that the response time, perhaps to maybe inadequate replies to 483s and warning letters, is pretty delayed. And it also, what it does is it slows down the ability of the commitments to actually be implemented. So everything moves at sort of a slower pace when it comes to the generics and OTC industry, because any kind of commitments, usually which are for improvements, usually impact the profitability of the organization because it costs something, and it's a pretty low margin business to begin with. So because of that, there's a bit of a desire to delay the implementation and to delay the cost of these improvements that they may be either forced to do or have made commitments to do. And so for this industry, the low cost is really more valued than is FDA's opinion, and that's what they think of as just FDA's opinion on what high quality is. And so with this lower cost business, sometimes the implementation of changes is delayed as long as possible. Now, another issue associated with the CGMPs is this business called benchmarking. And the concept is that if you ask around and everybody seems to be doing it a certain way, and they seem to be not being nailed by FDA for doing it that way, then it must be okay. And so that's called benchmarking, and what it means is that you have consensus manufacturing. Manufacturing developments and technologies are based upon the lowest common denominator, what most people tend to be doing. Whenever you have consensus manufacturing, that means that the desire for innovation tends to be stifled. You tend to do things the way that the run-of-the-mill is and not the way that the front leaders are doing things. And part of the reason for that is that innovation inevitably creates tougher expectations. Once an innovation becomes not even commonplace, but becomes desirable, then FDA, because of the little c of CGMPs, now expects everybody to do it that way. And so if you happen to be a non-innovator, one who's operating a relatively low-margin business, and these improvements cost money, you're not too inclined to want to innovate to better and better ways of doing things that might actually improve the safety or the quality of the medicine, and may even reduce the long-term cost of something. The problem with that is that there is an immediate cost. There is a high short-term cost, and because of that short-term cost, there tends to be very slow industry-wide adoption of these innovations. So if you're not going to be in the innovation business, then you don't need to have innovators on the payroll because they're not needed to do anything. And if you have fewer innovators around, then there's less scientific reasoning going on. So with fewer innovators, that means you can maybe operate with fewer employees and maybe even cheaper employees because the qualifications might be actually lower. So what happens is that scientific reasoning winds up ultimately being replaced by tradition, the way we've always done it. Now, I want to tell you a story. It's called the baked ham story. It's purely fictitious, but it demonstrates the point. Okay, imagine, if you will, a mother is preparing a baked ham for a family dinner at Grandma's house. And the mother's daughter is standing there watching her intently as she prepares the ham. And what she sees the mother do is she sees the mother cut off the end of the ham, the little pointy end of the ham. She cuts it off and then wraps it in the foil, puts all the stuff inside and sticks it in the oven. And the little girl who's watching her mother do this says, "Mommy, why did you cut the end of the ham off?" And the mother says, "Well, I've been baking hams like this ever since I was only just a little bit older than you. And my mother your grandmother, always cut the end of the ham off. And I want you to know those were the juiciest, best-tasting hams that we ever had. And so I am continuing to do exactly the way she did it so we can have good-tasting, juicy hams just like your grandma made. And the little girl asked the inevitable question, why? And so the mother says, well, it has something to do, I think, with the juices, there's something, maybe there's something that may not taste good in that end that I cut off, and so anyway, it's something like that. And the little girl says, are you sure? And of course the mother says, well, I'll tell you what, when we get to Grandma's house, you can ask her why that works. And so, sure enough, after all the food is baked and wrapped up and loaded into the car, and the kids and toys and everybody's loaded in the car, and everybody heads over to Grandma's house for the big family dinner. All the food's being unloaded, and the little girl goes up to her grandmother and says, Granny, how come cutting off the end of the ham makes a baked ham taste so good? And the grandmother says, what? Well, Mommy says that because you cut off the end of the ham, it makes it taste better. And the grandmother says, that's what she told you? She says, yeah, that's what she told me. Oh, honey, let me tell you what the story really is. When your mom was growing up and living with us here, we didn't live in this house. We lived in a smaller house that's, a few miles from here. And we didn't have a very big kitchen, and in that little kitchen was a tiny oven. And because the oven was so small, I had to cut the end of the ham off in order to fit it into the oven. And that's the only reason I cut it off, was just so it would fit into the oven. So, here we go. Traditions sometimes may be based on successful practices that may be used without really understanding the underlying mechanism. It may be, like in the baked ham story, based on some misperceived cause of some observed phenomenon. Maybe it's from some unscientific opinion or edict that comes from management. That's been known to happen. Sometimes it's just a misinterpretation or an exaggeration of what is perceived to be a compendial or regulatory expectation. There may also be a belief that has been held on for years and years from some antiquated concepts that have long since been revised or updated or even deleted and found to be untrue, but yet you still hang on to the way things were done. And of course, sometimes traditions are based upon benchmarking. And that's, the concept like we explained before. If everybody else is doing it, it must be okay. So you don't need very much thought to be able to manufacture by consensus. All you need is a good polling organization to find out what everybody else is doing, and you just go along with the mob, do what everybody else is doing. So, as everybody knows, there's a reason for a tradition, right? Well, maybe not. I got this graphic from www.despair.com. Worth visiting. Good website. Here's this picture of the running of the bulls. And it says, tradition, just because you've always done it that way doesn't mean it's not incredibly stupid. So, take that for what it's worth. When you replace scientific reasoning with just tradition, the way we've always done it, then you're opening yourself up for some problems. What happens is that in our industry here, we tend to create rules because we operate by rules. And they're created basically by precedence. If we've always done it that way, then that's the way we're going to continue to do it. And actually, rules do make compliance better because people, all they have to do is know the rule and obey the rule, get trained on the rule. They don't have to understand what the rationale is behind the rule. They have to just be good soldiers and obey the rules. Often employ obedience to of the rules is favored over the scientific competence or experience or education or even critical thinking that they may actually have. Obedience is preferred. And so what often happens with these rules that become established, and they are in play for so long, is the original establishers of the rules are long gone, long since retired, maybe died. And so there's no one to go back to to ask, how come? And so the basis of the rules is long forgotten, and after you've been doing it for a long time, it's unquestioned. It's just the way it's being done. So what this does is it results in a rule-hungry corporate culture that winds up being driven by precedents and also by benchmarking. And so scientific ignorance of the basis behind these rules starts to become prevalent, and critical thinking becomes a lost art. The experienced and educated employees wind up feeling very unappreciated because they're not needed. They're never asked their opinion, and frankly, because they are experienced, that means that they've been around for a long time. And if they've been around for a long time, they're pulling down a pretty high salary. And so either they're going to retire or perhaps quit, perhaps out of disgust or whatever. They may be rationalized or reduced if there's some sort of cost-cutting measure that comes in. The ones who make the highest paychecks are usually on the block as the first ones who will be retired. What's the impact of all that? Well, you get larger profits because your compensation budget is smaller, which is often the largest portion of an operation budget. But what you get out of that is the overall experience level drops. Even if you didn't replace these folks that you let go with lesser experienced people, just the fact that the experience is gone reduces the overall experience level of the workforce, and that includes in management. So what often happens in order to backfill these positions is that you may relax the scientific and educational expectations. This makes management actually a little bit happier because there's fewer people who know enough to be able to say nay or rock the boat. And in a lot of places you start outsourcing some of your formerly internal services. And when you start doing that, you start to lose control over the quality of those services. And that's all great for the short-term bottom line. It allows you to operate on a lower budget, but it is a ticking bomb. Sooner or later, you're going to have a very costly problem that's associated with this reduction in workforce and reduction in experience and reduction in competency. It's going to come back at you. So, water systems are not immune to this concept. They operate on a rule-based culture. The rules for engineering and design are very well ingrained into many engineers. There are just certain ways that you do things, certain flow rates you have to have, certain absences of dead legs, and we'll get into a whole bunch of things that are just rules without this understanding of what's behind that rule. But rules are also the basis of how things are done in a laboratory. Remember, things are all done by SOPs, and SOPs are nothing more than rules. They're just complex instructions on how to do things, which are in essence a complex rule on how to do something. Sometimes the rules develop because they're misapplied out of context from some other location. Sometimes they're like from a misinterpretation of a phenomenon or misextrapolation of a reference of some sort. Sometimes they're created from these old traditions because they've always been done that way, even though the tradition or the basis behind the tradition is no longer even applicable or acceptable, the practice continues. Sometimes, and I hate to admit this because I do see this, sometimes the rules are either created or bent by technology vendors in order to get you to buy something. to increase their sales. And so you got to be careful when you listen to vendors when they tell you, oh, well, you got to have this because if you don't, less than so is going to happen. Just be careful because that may not be completely factual. Nevertheless, rules become common practice, and no one is the wiser. The rules wind up being unchanged and unchallenged over a long period of time, and eventually they evolve into what I call water myths. So, water myths ultimately lead to poor design and poor practices, and whenever you have poor design and poor practices, your problems are going to increase, and if your problems increase, your costs are going to increase. So it really sort of ultimately leads to a foolish endeavor to control costs by ultimately creating water myths that lead to poor practices that ultimately increase cost. So it's almost getting exactly the opposite effect of what you want in the long term. So we're going to talk about two types of myths. We're going to talk about microbial control myths for water systems, and we're going to talk about testing myths for water systems. And there's a whole boatload of each of these. We're going to get into some of the microbial control myths. Now we'll start off with this first one. Water for injection that's made by reverse osmosis. Here's the myth. WFI cannot be safely or validly produced by reverse osmosis or other membrane technologies. That's wrong. Absolutely wrong. The EMA, used to be the EMEA, but the EMA and the EP are absolutely dead set against water for injection being produced by reverse osmosis. They consider distillation to be the only reliable method, and it's got a long history of reliability, but it is not infallible. I have had many consulting projects, more than you can count on one hand, of situations where distillation or stills have not been able to protect against the carryover of endotoxin, which it's supposed to be an absolute barrier for. I've had many situations where that has not happened. So it is not infallible. These opinions, at least this is my belief, that these opinions are really based on really the old problems that used to occur with the old RO designs. Now, make no mistake, there are still those old RO designs that are still being used today. They tend to be the cheaper reverse osmosis systems. But the old RO problems were the only problems that you had back 10 and 20 years ago. But nowadays, ROs have improved greatly. But back then, ROs were notorious for leakage and poor seals. They obviously weren't integrity testable. They actually were not an absolute barrier. They were a sort of a percentage removal process. And there were other issues associated with chemical sanitization because an RO is actually working in the way it ought to. The sanitant would have to penetrate to the downstream side or the permeate side of the membrane in order to sanitize that side of the membrane. And the vast majority of the sanitizers can't do that. And so there was a problem with sanitizing 100% of the RO, including the permeate sides of the membrane. Also, this opinion on ROs being problematic didn't consider that nowadays, like for the last 5 years at least, there has been hot water sanitizable reverse osmosis systems. They've got a better set of materials of construction and bonding and whatnot that allows hot water to actually be flowed through a reverse osmosis system and hot water sanitize it such that nothing will survive. And that absolutely, totally, 100% controls the biofilm that might actually be growing on either side of those RO membranes. Also, in order to sort of, I guess, support their point, there was a reflection paper that was written by the EMEA, and it contained a lot of inflammatory and exaggerated statements that were largely inaccurate and scientifically weak. And a lot of organizations have responded back in a negative fashion to that particular paper, but nevertheless it still stands, and it's still used as the basis for the EMA and their regulations to this day. The question is, what motivated this? Was it ego? Was it politically motivated? You know, the regionalistic thing, we're tighter on our specs than you are, so we're better, you know, that type of thing. We don't know. All we know is that it still stands to this day. Now, if you read USP, were in the preamble to the WFI monograph, it basically, and this is sort of a paraphrase, it says that any technology is allowed to produce WFI as long as it is equivalent or superior to distillation in the removal of chemicals and microorganisms. Now, those are words that were actually requested by FDA to be placed in lieu of what USP's opinion was, which had to do with, you know, any technology can be used as long as it's validatable, and that's the essence of it. But we acquiesced and said, okay, just have to demonstrate that it's at least as good as distillation for the removal of chemicals and microorganisms. Now, there's also a bit of a misnomer here, and that is that anybody who knows about water system design knows that it's not just a reverse osmosis unit that's involved in the purification process. If you do have an RO involved, almost invariably there's pretreatment before it, so you don't scale up and ruin your RO, and usually there's a deionization step right after the RO because you can't get the purity that you need just from even a 2-pass RO. So there's often either plain bottle-type DI or electrodeionization of some sort, and perhaps even ultrafiltration downstream of that to remove any residual endotoxin that may not have been pulled out by the previous 2 steps. And so you have RO, yes, in the train, but it's not the only unit op in the train, and it's not even the last unit op in the train. So it's a bit of a misnomer to say that WFI is produced by reverse osmosis. It's produced by reverse osmosis plus a bunch of other things. So it's really not fair to focus on the RO as a weak link, because it really isn't weak. The high temperature operation that we now can have with reverse osmosis allows very good sanitization and completely eliminates any kind of biofilm that may be growing on either side of the membrane or within the RO unit itself. And so this eliminates any microbial or endotoxin contamination being produced and originating on the downstream side of the membrane, then going forward into your process. You still are going to need to have the sensors and the alarms and the divert plumbing and all that stuff, just like a still would have, in order to make sure that bad quality water wasn't put into your distribution tank. So you still need to have those same kind of controls. And there's actually been a number of published examples where water being made by processes other than distillation for manufacturing WFI have exemplary records of control of endotoxin and microbial count and chemistry and so forth and so on. I participated in and actually helped craft a survey that was put out by ISPE and is published in the November-December 2011 issue of Pharmaceutical Engineering, the survey results. And this was a survey of users who were not using distillation to produce water for injection quality. And it was a survey of what kinds of processes do they actually use and that have been successful. And the bottom line is that there is a plethora of ways of producing water for injection that very well control the endotoxin and the microbial content of the water. And it's not just any one technology, it's any number of technology and combinations of technology that can work just as well and often more cheaply than the distillation process. So if the science and the economics of these alternatives are allowed to be used and explored and examined, then eventually that will win out over the egos and the politics that may be the obstructions to the adoption of reverse osmosis and related unit operations, to the making of WFI, any technology other than distillation. So let's get on to the next myth, turbulent flow and flow rates. Lots of myths on this, just ask an engineer. Here's the myth. The turbulent flow with Reynolds numbers greater than about 4,000 and high flow rates, these are rates greater than 3 feet per second, will prevent microbial attachment and biofilm growth. Well, guess what? That's wrong. This myth actually originated from the observation of the microbial count differences between a stagnant water system and a recirculating water system. And so this was extrapolated to have been caused by non-turbulent conditions versus turbulent conditions. So what the actual cause was that in these less turbulent conditions, biofilm tends to grow in a more erect, upright form. Let's call it a fluffy form. It's very fragile when it grows that way, and it can only grow when there's low shear. But it is very shearable. It's very fragile. But if water is flowing, the biofilm doesn't grow that way. If the water is flowing at a high rate, the biofilm that forms is more tenacious and more lower profile. It doesn't stick up into the moving water column, because anything that would get sheared off immediately. And so what you wind up with in a high flow situation is a very tenacious biofilm. So very resistant to the shear forces of the water. What happens when you sample these two systems is that you create high shear forces right at the sample port. So right where the water is coming out of the system into your sample container, there are high shear forces. And so if you happen to have a stagnant system that you now open a valve and cause a great deal of flow through a portion of the system and down that sample valve and into your sample container, you're going to shear off all of this fluffy biofilm, and it's going to come into your sample container. But if you are collecting the same sample from a system that is rapidly flowing and has tenacious biofilm in it, the shear forces that are exerted at that outlet shear off very little, because all the biofilm is already tenaciously holding on to that surface. And so you get low counts out of a high shear system and high counts out of a low shear system. So the misinterpretation then is that when you get the higher counts from the stagnant water, the misinterpretation is that the higher counts are because there's more biofilm growing in the stagnant water. But that's not true. Biofilm grows strictly at a rate that's related to the nutrient level. It has nothing to do with the flow. So the microbial attachment will occur regardless of the flow velocity. And that's because there is a boundary layer right next to the pipe. And the boundary layer is thinner or thicker depending upon how fast that water is moving. And so the boundary layer exists on every single surface in that system. It exists in the straight parts of the pipe. It exists in the elbows. It obviously exists in little side legs. There's boundary layers everywhere, and they are of different thicknesses. And when biofilm grows, it always grows within that boundary layer. That boundary layer is where the flow is laminar. It's a leisurely flow. It's not turbulent. It doesn't have high shear forces when it's a laminar flow like that. And so within the boundary layer, that's where the biofilm is actually going to grow. And anything that sticks up above the depth of that boundary layer is going to be susceptible to shear by the forces of the water. Now, when it is the water is continuously and rapidly moving, it actually reduces the amount of planktonic shed that the water system has of the biofilm organisms being sheared off into the water, into the planktonic phase. And so with a rapidly moving system, the actual planktonic counts in that system tend to be quite low. With a slow-moving system, the planktonic counts tend to be much higher because whenever you actually grab a sample, you create the shear forces of the movement. So rapidly moving water does actually not reduce biofilm development. It grows at the same rate as a function of the nutrient level that is there. It has nothing to do with the flow rate. So in two systems, one that's stagnant and one that is rapidly recirculating, you're going to get biofilm development and microbial biofilm growth at exactly the same rate. The difference will be what the biofilm looks like. It'll be its structure. Okay, let's move on to dead legs. There are some dead leg rules. You've probably heard of the famous 6D dead leg rule. And this describes the maximum side leg length that will avoid biofilm formation. That's your myth, and of course it's wrong. It's actually been a misapplied concept that originated back with the milk industry, believe it or not. Originally, the milk industry used hot water and other cleaners to sanitize the stainless steel piping that was associated with the milk distribution systems, milk processing systems. And so they had to clean out these pipes, and they found empirically, by practice, that if a side leg was longer than 6D, D being the internal diameter of the side leg, and the 6 is measured from the center line of the main pipe off of which this little side leg goes, and 6D is the maximum length that little side leg can be, that actually allowed the cleaning of the stainless steel milk piping with hot water or cleaners or whatever. If it got longer than that, you would not effectively clean out the milk residues off the surface of the pipe from that little side leg. Well, as I mentioned as a possible thing, that developed and was commandeered by the pharmaceutical industry as a design rule. 6D is a design rule that would prevent biofilm formation, which was never what it was intended to be for. It was a cleaning thing. Now, there are other dead leg rules that exist. There's 3D, 2D. You pick the D. There's a rule. And it's also claimed to avoid biofilm, but they're also wrong. There are even 0 dead leg valves that have no dead leg whatsoever claim to avoid biofilm, and those are still wrong. If the conditions would allow microbial growth to occur, in other words, not hot and not continuous ozone or something like that, then biofilm will grow in a 0 dead leg valve. No side leg length can avoid development of biofilm. Short is better than longer, that's for sure. But it cannot be so short that biofilm can't form. Now, you do have more turbulence that occurs with shorter side legs than with longer side legs. And you do have somewhat less shearable biofilm that might occur with some turbulence getting down into the side leg. But actually, most of the effect of the dead leg is really to allow the mixing of sanitizing conditions down into that side leg, much akin to the original purpose with the milk industry. It is not related to shear forces. That's been the unfortunate phenomenon that has been claimed to be the benefit of shorter side legs, and it really doesn't have much impact. Now, some systems, even though you don't want to have dead legs in your system, sometimes some dead legs are relatively difficult to completely eliminate just because of the nature of the equipment that's attached to it and so forth. even a bona fide dead leg can be addressed with regular flushing. Remember, what happens in a dead leg is biofilm tends to grow in that dead leg, and so you can get rid of the biofilm literally by creating the shear forces that would otherwise not be exposed to that down into that dead leg with regular flushing and regular sanitization of the side leg, which would no longer be a dead leg because it's no longer dead. You actually create flow in it. And those strong flushing forces will create the shear force that will shear off most of the fluffiness of the biofilm, leaving the tenacious part behind. It will also allow you to flush sanitant into that dead leg, which has at least the opportunity to kill the developing biofilm. But that killing, and I have a whole webinar based upon sanitization, but that killing is based upon the thickness of that biofilm that's been allowed to develop between treatments and how aggressive the sanitizer condition is, which is related to its oxidation potential and concentration and contact time. And just be aware that a thick biofilm will rarely be completely killed or removed by any kind of chemical sanitant. Hot water can completely kill it, but it will not completely remove it. And if it's not removed and left in place but dead, it will become food for biofilm regrowth later. So let's move on to the next one, smooth hydrophobic surfaces. The myth is that smooth electropolished stainless steel can reduce the initial cell attachment and therefore cause less biofilm development. Well, as you might imagine, that's wrong. How about smooth hydrophobic plastic surfaces like PVDF? They're claimed to reduce biofilm development. That's also wrong. What you actually get is a delay in the attachment of the organisms to that surface, not a complete elimination of attachment. It just delays the attachment, perhaps by minutes to a few hours. And if you think in the whole scheme of things of how often you sanitize a water system, minutes to a few hours makes little difference in the amount of biofilm that actually initiates on that surface. And actually, once biofilm has begun to form, the surface of the biofilm becomes the preferred attachment location, not the material of construction, but organisms tend to want to stick into another existing biofilm. It's the preferred attachment location. So it's questionably worth the high cost of electropolished stainless steel or PVDF if you're trying to reduce biofilm development. Now, the smooth surfaces are indeed easier to clean. You can, with the absence of scratches and micro scratches and whatnot in the surface like you get with a stainless steel grit finish, you can have more cleanable surfaces, less hills and valleys to have to clean down into, fewer areas where organisms can hide away from the chemical sanitizers. And so there is a cleanability issue associated with smooth surfaces, but it is not related to the development of biofilm. There are actually some active research projects going on to create biofilm-resistant surfaces in devices that are implanted, because the greatest risk of infection from operations involving implanting medical devices is from the organisms that are introduced during the operation. And those organisms, if they find the surface of that device and start to grow on the surface of that device as a biofilm, you will never get rid of those organisms with antibiotics. And the only way to get rid of them is to replace the device. So now, as a preventive, they are impregnating antimicrobial compounds into the surface of these devices that slowly leach out into the tissues and eventually completely leach away. But it at least protects the patient for the first few weeks after the device is implanted, which is the most risky time. Obviously, if you had something that leached something from its surface, you could never use it in a water system. You'd be failing your TOC in no time, or some other things that become an added substance in your water, which, of course, you couldn't have. Okay, let's look at periodic sanitization of 80-degree C systems. Now, believe it or not, there is this perception that no matter what the system operates at, it needs to be periodically sanitized. And this includes 80-degree systems. And so here's the myth, that since all water systems should be periodically sanitized, continuous ADC distribution loops should be periodically sanitized with even hotter water or steam. Now you can imagine, that's wrong, absolutely wrong. There are no organisms that actually grow in high purity water that need even hotter conditions to be killed. Nothing can grow at ADC, let alone survive long enough in order to have to be killed by a higher temperature. Well, water temperature at ADC is continuously lethal to all the kinds of organisms that could grow in a water system. Studies have been done on D values at various temperatures, and I'm not giving you the reference here, I'm just telling you for your information. At ADC, the D value for Pseudomonas aeruginosa is on the order of about 5 milliseconds. That's the D value. So within a second of exposure time at ADC, you have killed umpteen logs of possible organisms. And aeruginosa is pretty typical of the kinds of biofilm organisms that you're going to find in a pharmaceutical water system. And so they're all very, very susceptible to heat. There is no need to treat these water systems at even higher temperatures. Now, an ADC system doesn't necessarily mean that it's ADC everywhere. It could have points of use that are cooler, that never experience a temperature, although if it's stainless steel, more than likely the heat conduction is going to carry enough of that heat down into the distal parts of valves if they're stainless steel. But if you have a plastic system, the heat won't conduct the same way. So if you do happen to have point-of-use valves or other kinds of valves that are cooler than the actual circulating water behind them, then all you got to do is flush that 80-degree water through that valve just for a few seconds. Obviously, with organisms that die in milliseconds, it doesn't take more than a few seconds at that temperature to kill those same organisms. Okay, let's talk about inline sterilizing filter. There is a myth that inline 0.2 micron filters remove all bacteria from the water. It's wrong. Even though they're sterilizing grade filters, and even though they're considered to be absolute filters, they don't remove all the water, all the bacteria, especially from a water system, because the water bacteria are a little special guys. There's another myth that 0.2 micron filters are not allowed by FDA. That's wrong. They are. There's the phenomenon here of microbial penetration is called go-through, grow-through, and blow-through. Go-through is where the organism actually winds up finding a larger pore and gets through the pore without impinging on the media or permanently sticking to the side of the media as it goes through the tortuous path and gets through to the other side. This has been shown to happen in pharmaceutical water systems with pharmaceutical organisms that are growing in the water. Ralstonia piquetii is an example of an organism that can actually go through a filter, especially when you have a higher concentration upstream side of the filter. Then there's the grow-through phenomenon, still contested as whether or not it actually occurs, but hypothetically what happens is that the organisms impinge on the surface, and over a long period of time, as the biofilm develops from these organisms, growing on the nutrients that are absorbed to the surface of the filter, basically a colony, if you want to look at it that way, of organisms will grow all the way through the tortuous path to get through to the downstream side of the filter. Now, even though the filter may even be a fraction of a millimeter thick, to a bacteria, it's like a gauntlet of 100 yards of trying to make it through, but give it enough time and it will do it. And enough time generally is on the order of a week or two. Then there's the blow-through phenomenon, and blow-through is a real phenomenon. It's what happens whenever you have intermittent or pulsed flow. on a filter. With the surge of flow through the filter, you flex the matrix a little bit. Any organisms that have impinged on the filter elements could be released by the surge of flow, only to be re-impinged a little bit further down in the filter. But as they work their way through the filter with successive pulses, they will eventually get through to the other side. This happens with peristaltic flow going through filters, and also happens with intermittent on-off operation of filters. So be careful if you don't have continuous flow going through your filter. If it's intermittent flow, you set yourself up for the possibility of forcing organisms to go through. Long-term service of the filter is one of the hallmarks of what causes that. FDA does expect filter use to be validated. They want that period to be determined because they know that the longer a filter is in service, the more likely organisms are eventually going to get through that filter. In some situations, it could be a matter of hours. In other situations, it could be weeks. But eventually, organisms will get through. So if you ever use a 0.2 micron filter in line in a water system, make sure you have determined how long it takes before organisms get through that filter, because it may be less time than you think. It may be only a week or two, and it's not uncommon to see filters that have been in service for perhaps years because they haven't reached some magic delta P that would trigger a filter replacement. If you were to put UV sanitizer upstream of the filter, you could greatly extend that use period to perhaps a half a year or even a year, because the only organisms landing on the filter would have already been killed by the UV. There are some 0.1 micron filters that will not allow microbial penetration. I say some because not all 0.1s will keep bacteria from getting through, but many of them will. The problem with some of the design of some of the 0.1s is that they tend to be more costly than more expensive filters. There tends to be, but not always the case, but tends to be a reduced flow rate because the filter's tighter, and so the amount of flow going through is impeded by the resistance of the flow, and so you're probably going to need a larger number of 0.1s than you would if you had 0.2s, and this is much more expensive. So there's an expense issue associated with using 0.1s, although a lot of folks do that. Now, for microbial control, no filters, and we're even talking about the really coarse filters, the 5 micron filters, no filter should solely be changed based upon the delta P or the pressure differential across the membrane. They should all be based upon a service time plus a pressure differential if it happens to trigger before the service time. So it could be a combination of the delta P as well as service time, keeping in mind how long it takes for organisms to actually get through a filter. Now, obviously, a 5 micron filter is not designed to hold bacteria back, but what it does is it can be basically a solid-state fermenter, if you want to call it that, where it grows biofilm on the surface of the 5 micron matrix that's in there. And eventually you'll be releasing more bacteria downstream than are actually impinging on the upstream sides. And so just be careful about long-term use of filters, no matter what they are, and never, ever, ever base it just on delta P. Okay, added substances. Ozone. Ozone is, here's a myth, ozone is an added substance and is not allowed in pharmaceutical water systems. Well, that's a myth. Absolutely wrong. Decomposition residues from ozone, where ozone is acting on biofilm or something, that are added to the water when these compounds degrade by the ozone, those are considered added substances and are not allowed in water systems. That's also wrong. And these two things are the primary reasons right now for the slow adoption of ozone being used as a sanitant in water systems. And it's all mythology. It's all mythology. Ozone is a great sanitant if it's used properly. And so if more places used ozone, there'd be way fewer problems. It is not an added substance if you remove it from the water with UV, and it's really easy to do with UV, before you use the water. So it can't be added if you unadd it, if you take it back out before you actually have the final water. The residues that ozone creates when it attacks organics are just the same organics that were there all along, and so they're not added substances. They're more than likely they're going to be at some undetectable or low concentration anyway, and lower than what you're actually measuring in your water. You will not see a TOC difference whenever you do it. It'll certainly not increase. It may decrease with some of the organics being converted to CO2. And so you got to understand that added substance rule that now exists in most of the monographs in USP originally was created way, way back at the time when bacteriostatic water for injection was put into the monograph. Bacteriostatic water for injection is only it's sterile water for injection that has had a preservative added to it, and it's used for multi-dose dosage forms, often like vaccines and things like that. And so the no added substance was created in order to distinguish between bacteriostatic water for injection and regular water for injection, because bacteriostatic water for injection did have an added substance. Okay. Anyway, the whole concept of added substances has been extrapolated way beyond its original intent. Okay, now let's go into testing myths. We do have a few of these. Let's talk about referee methods. Referee methods are the method of choice for doing something. There is a perception that the water micro methods that are listed in USP, EP, and JP are referee methods and must be used for those particular waters. So if you've got EP, you've got to use the R2A 30 to 35, no less than 5-day thing. That's their referee method, and if it's JP, it's similar to that. If it's USP, it's the 2 or 3 days, plate count, auger, 30 to 35 degrees. Those are the methods that are listed. However, it is wrong to think that. The reason is, certainly for USP and JP, those methods are listed in their informational chapters. Informational chapters are not mandatory. They're not obligatory, and they're certainly not referee methods that would be the courtroom method, the official method in a court of law whose results would make the difference in the ruling of a court case. Now, EP's methods are actually in the monographs for purified water, water for injections, and highly purified water. And it is a referee method because it is in the monograph. And therefore, because these referee methods are the method of choice for the courtroom, there is the thought that you actually have to use that method. And in actuality, that is untrue. And that's because all of the pharmacopoeia allow methods that are equivalent or superior to be used in lieu of the referee methods if they can be soundly documented as being equivalent or superior. In other words, if you can prove that you have a better method with some sort of formal study, then you are perfectly allowed to use that method for your water system and for your particular application. However, if it ever came to a court study, the method of choice in the courtroom would still be the referee method, but since you've already shown that your method is better than the referee method, then you are ahead of the game. So what means better? What is equivalent or superior? What does that mean? Well, with a water test method, it means that you've got at least the same number and types of organisms as the reference method, or that you have significantly higher recoveries or more types, or that you can see the same results in a shorter period of time. Okay, let's now talk about thermophiles in hot water systems. Now, we do know as a fact that the environmental conditions of any particular habitat tend to select for those populations that can best flourish and survive in that habitat. That happens everywhere. Extremophiles exist in salty alkali lakes and hot springs and volcanic vents. These are organisms that are particularly suited for growing in these extreme environments, hence the name extremophiles. Therefore, one might expect that a hot pharmaceutical water system would select for colonization by thermophiles, but that's wrong. It doesn't. Why doesn't it? Because all the aquatic thermophiles that are known to exist have very fastidious, exacting nutritional requirements that are not found in pharmaceutical water. There's a reference that's listed right there by Martinez that talks about every single known hypothermophile and what its nutritional requirements are, and not one of them could have a chance of living in a pharmaceutical water system. So the bottom line is that thermophiles do not exist in hot pharmaceutical water systems. So please do not waste your resources testing for thermophiles. And if you have some unreasonable expectation from an auditor or even from FDA, fight that request with science. Reference that article. Do whatever you can to avoid this senseless testing and waste of resources, because thermophiles do not exist in these water systems. Okay, here's one of my favorites. R2A, 35 degrees, 5 days. Those of you involved in water testing know exactly what that is. Those are the testing conditions that are often used when trying to comply with EP waters, be it purified water or whatever. And therefore, there is this perception, excuse me, there is this perception that is the best set of micro-test conditions that you could use for your pharmaceutical water. Well, guess what? That could be wrong. I'm not saying it is wrong. I'm saying it could be wrong. Now, you got to understand that those particular parameters, especially the temperature and the incubation time, are not what are the EP method conditions. The EP method says 30 to 35, not 35. And it says no less than 5 days. It doesn't say 5 days. You may find that a lower temperature recovers better organisms. 30 degrees works better than 35. You may find that 7 days is better than 5 days. But people tend to use what they perceive to be the hottest temperature that will get the fastest growth in the shortest amount of time. Hence the 35 degree and 5 day usage, which is very common. This has actually been conditions, and it's often quoted that these came from standard methods, but they don't. If you were to look up the standard methods for drinking water, you would find that a lower temperature is specified. A temperature of 20 to 28 degrees is what's actually specified in standard methods. And the incubation time is 5 to 7 days. Not just 5 days, 5 to 7 days. And this is for drinking water organisms. And remember that pharmaceutical water is very, very different from drinking water. Drinking water has well-developed biofilms growing in the pipes that have never been sanitized, never. The pitiful sub-ppm levels of chlorine flowing through the water do nothing to attack the biofilm. There are much higher nutrient levels in drinking water. There is much higher microbial diversity, mostly because of the age of the biofilms. They've been around for decades. You do have chlorine stress because of the chlorine floating in the water. And so R2A, which was actually designed and devised in order to recover chlorine-stressed organisms, not oligotrophs, but chlorine-stressed organisms, R2A is probably the optimal medium for drinking water. However, it may not be optimal for pharmaceutical water because pharmaceutical water is pure, it's frequently sanitized, and so you really ought to do a study where you evaluate perhaps several different media, high nutrient and low nutrient media, against a variety of temperatures, because maybe 35 isn't the best temperature. Maybe cooler temperatures will work better, especially if you're in some of the northern latitudes and your water systems never get above 20 or 21 degrees. What's the chance of you having optimal recovery at 35 degrees incubation when your water system is never higher than 20 or 22 degrees? Obviously, you're going to select organisms that prefer that ambient temperature of 20 or 22 degrees. And 5 days may not be the best incubation duration for your particular medium. You may need to incubate it longer, particularly if you incubate it at a cooler temperature. It will take longer to grow these organisms. So the ideal test conditions are really ones that give you the highest recovery in the shortest amount of time. And every water system is potentially different with potentially different flora, because everything that you do to a water system, including its starting water, has an impact on the flora that eventually develop in that water system. And so you may find that R2A at 30 to 35 degrees for 5 days is best, but in my personal experience, I have never seen a difference in the finished water between R2A and TSA or plate count auger or whatever at the optimal temperature, usually 30 to 35 degrees, and often you can see test results in 48 to 72 hours, which is a whole lot better. Okay, let's look at test filters. Now, there is a knowledge, of course, that there are very small bacteria in water. And since we already know that these small bacteria can actually easily pass to some degree through a 0.45 rated membrane, that your testing for water ought to be done with a 0.2 micron membrane. That's wrong. Millipore actually did a study, and they didn't even use water organisms. They used a battery of challenge organisms. And the way it turns out is that 0.45 micron membranes will actually allow some percentage of all kinds of bacteria to get through. But it only allows maybe 1 in 1,000 to maybe 1 in 10,000 of the organisms to actually get through, which is certainly not exclusive enough for a 0.45 to be used as a sterilizing grade membrane. But from the standpoint of a testing membrane, where your accuracy is never within a tenth of a percent or even 100th of a percent, it has an insignificant impact on the accuracy of the test to use a 0.45 micron membrane. Actually, what they have proved in their studies is that these tighter membranes, the membranes are now at 0.1 or even less, tend to be slower in their allowance of nutrient diffusion and waste diffusion through the membrane. And so these tighter membranes actually are poorer surfaces for organisms to grow on because they don't allow as free an exchange of nutrients and wastes as are found in 0.45 membranes. So actually 0.45s are far better for testing it. And this is, by the way, in case most people don't realize this, the actual rating, the 0.2 or the 0.45 that's rated, is not the pore size of the membrane. It's not at all. The actual maximum pore size of any given membrane is probably somewhere between 2.5 and 3 times the size of that rating. So if you had a 0.2 micron membrane, your largest pores are actually on the order of about 0.5 microns. So plenty large enough for some organisms to be able to actually find the big holes and get through. And that's why water organisms, which have a lot of really small organisms in them, those water organisms can easily eventually get through, especially if there's high numbers on the upstream side. That's why the go-through phenomenon exists. Okay, compendial action levels. You have heard and see published compendial action levels of 100 CFU per ml for purified water and 10 CFU per 100 ml for WFI. And therefore, these should be used as your action levels for microbial control. And that is wrong. Now, we're talking about action levels in the true meaning of the word action level, which is not a specification, but a level that tells you you need to do some in-process control remediation. If you look at Chapter 1231, you will see that it says that these numbers are the maximum action levels that should ever be considered for use. But lower is probably better. A trend-based lower number is better. If you look in the EP purified water and water for injection monographs, you're going to see that these action levels are actually in the monograph. Now, if it's in the monograph, it doesn't matter if you call them action levels. They are truly a specification. They are mandatory. They are a pass-fail number. They are not a point at which you can take action to bring things under control, otherwise everything's okay. No, everything is not okay. If you exceed these levels, you have, for all intents and purposes, failed the specification. So in spite of the fact that the name and the word action level is intended for process control and not quality control, finding it in the monograph makes it a quality control specification. And in fact, regulatory interpretations are that those numbers are specifications. Why else would you be expected to do an OOS investigation if you were to exceed those numbers? What does the S stand for of OOS? Specification. And what's a specification? A pass-fail number. So these numbers might wind up being basically way too high to be a functional microbial process control indicator. So your biofilm is probably well out of control by the time you reach that number. So regardless of where you find it in the compendia, whether it's an informational chapter or in a monograph or whatever, you need to consider those numbers as your pass-fail specification because the regulators certainly think so. A well-controlled water system should have action and alert levels that are established based upon the trends of the actual water system, with the alert being something that's a little bit abnormal, higher than you normally would see, and action levels being high enough to say, okay, I really shouldn't ever be seeing anything that high. And these numbers are probably well below these compendial action levels and allow you to actually take action before you exceed that compendial action level / specification. Okay, Chapter 62 in USP, which is really the tests for specified microorganisms being applied to purified water. Here's the myth. The USP 62 microbial limits test for specified organisms are appropriate for USP purified water, especially when used for oral and topical products per USP Chapter 1111. Well, that's wrong. There are no obligatory USP microbial specifications in purified water or water for injection. Nothing. There's no spec at all for micro in those monographs, and that's intentional. Now, if you go back, way back into the 90s, 1995 or USP 23 was when the implied specification for E. coli was deleted. It was in the 1990 USP, which was USP 22, where it said for its microbial content that you had to meet the expectations of drinking water. And the only microbial expectations for drinking water happened to be the coliform test. And coliforms were actually allowed, but they could not be fecal coliforms in drinking water. Fecal coliform is another word for E. coli. So you could not have E. coli in your pharmaceutical grade water, in essence. That's what that meant. But that was deleted back in 1995 with USP 23 because the chances of having E. coli getting all the way from your coliform-free water, because it's supposed to be drinking water coming in, which is coliform-free, it's not likely you're going to add it along the way, right? So if it's never there to begin with, you should never find it at the end. There are other tests in USP 62, tests for Staph aureus, E. coli, Salmonella, bile-tolerant, gram-negative bacteria, Clostridia, Candida albicans, and of course in Chapter 61 there's a total yeast and mold count. These are all things that should never be tested for in your purified water or water for injection because it is not possible for them to be there. You shouldn't be testing these organisms in your water. Now, notice absent from that list right there is Pseudomonas aeruginosa, because of the organisms found in Chapter 62, Pseudomonas aeruginosa is the only one that has a chance of being found in a high-purity water system. Only one. And so if you did have to test for anything, Pseudomonas aeruginosa would probably not be a bad choice because it does have a chance of being present there. But remember that these Chapter 62 absence tests that we're talking about are primarily intended for product testing, not raw material testing. If you actually read the chapter, it says the microbial examination of non-sterile products is performed according to the methods, blah, 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 blah. Products. That doesn't say non-sterile raw materials. It says products. Now, that's not to say that it can't be applied to raw materials, but it is certainly not required to be applied to raw materials. In Chapter 11:11, it continues to say the same things, and if you look at the drug substance or excipient expectations, there's no absence test at all. It's only a total count that's specified in Chapter 11:11. Now, raw materials that are prone to contamination can actually have tests referring to Chapter 62 for specified organisms in their monographs. And it actually does occur in a few situations. But most of the USP/NF raw materials have no microbial specification at all. I actually, at one point in time, this is a few years ago, did a survey and found that of the 4,518 USP/NF monographs, 71 of them, or less than 1.6%, actually had specified microbial absence tests in them. Now, 54 of those 71 were of natural origin, and so the absence test sort of made sense. That something is of natural origin and minimally purified, environmental organisms could very well be present. And among them might be water contamination organisms like E. coli or whatever. Okay. Only 17 of those were actually required specific absence tests for synthetic or highly processed materials. And that was because the monograph author's choice was to include them. It wasn't USP's choice. It was the monograph author's choice who submitted the text to USP. And so that obligation was carried forward. So there winds up being no general implication, really, that purified water or water for injection should ever be tested for the absence of specific microorganisms. No obligatory general requirement, okay? There is disagreement on how best to do the test, even if you wanted to do that. Would you use the enrichment step before you went to selective media? And if so, what would be the sample volume you use? And are you sure that TSB is not too rich for the organisms that you might be trying to cultivate? And alternatively, some folks actually just filter the water and plate it directly on the selective media of whatever it is. And if you were to do that, you would for certain compromise the recovery of your target organisms because they cannot handle these selective conditions. They are partially inhibitory to the organisms that are targeted as well. And so there's a certain percentage of those that will just not survive. So here, we're getting in the short rows here now. TOC and endotoxin as microbial count correlates. We've been wanting to find something that's really quick for a lot of years. And a lot of people think that since TOC and endotoxin come from bacteria, and TOC is also food for bacteria, that they can be used as rapid indicators for a microbial count. And that is wrong. TOC and endotoxin also come from upstream sources in the upstream of the distribution system, back in the purification unit operations, or even from the source water. And so when these two chemicals can come into the system from multiple sources and not just from the organisms that are growing in the distribution system, then you can no longer use these as correlates. It is a poor correlation at best. There are so many other factors that affect microbial counts and so many other factors that affect the TOC and endotoxin levels in the water that if you could get an order of magnitude correlation, you're doing good. And an order of magnitude correlation is nowhere near good enough. So we have gotten to the end of this presentation. And at this point, I want to give you a few helpful hints. I want you to go home and look for the rationale of why you're doing things the way you're doing them. Try to figure out why. If your rationale is, well, we've always done it that way, that ain't good enough. If you can find no documented rationale, then look for an explanation. Question the science behind it, and if necessary, even improve the practice. And after you have done that, write up your study and your rationale for the either unchanged or the new practice. Even if you don't change anything, you find out the reason why you're doing it a certain way, write it up so it can be found by somebody. Anyway, I want to thank you for your attention. I have come to the end, and I am now ready to accept questions, and I see a question has already come, but there may be some additional ones. Let me turn it back over to Sam and take it from here with some instructions from Sam.
Thank you, Terry. It was a wonderful presentation, and I thank all the participants for cooperating with us. As Terry said, it's time for the Q&A to begin, and I request all who have questions for our presenter to click on the Raise Hand option, which is a palm-like icon at the bottom of your participants panel to ask your questions verbally, or post your questions in the Q&A panel so that our presenter can read it out loud and then answer. For any reason, if you're unable to ask your questions using either of the two means I mentioned, please share it with me by chat, and I shall pass it on to our presenter to answer.
Okay, we do have one chat question that has come in already, and actually came in during the middle of the presentation. And that is, it says, can we direct this toward medical devices? Well, yeah, we can. You know, a water system is a water system. And medical devices do require at least the use of a purified water system. Depending upon the medical device and whether it's implantable and whatnot, you may wish to use something akin to water for injection for the medical device if the level of endotoxin on the device or in the device might be a concern. But, you know, if we're talking, you know, even though I've been talking pharmaceutical water systems, maybe I should have been saying pharmacopoeial water systems, because those are pharmaceutical as well as for medical device, as well as for biologics, as well as for cosmetics, nutraceuticals, you name it. They all use the same type of water. The organisms that grow in a water system, and that is mostly the reason why these myths originate, and that's to somehow control or enumerate the organisms that are in a water system. It doesn't matter. The bugs don't know what the water is being used for. All the bugs know is that here's this pure water. It's a challenge to grow in it, but you know, you select for those that can. And so it's actually irrelevant whether the water system is for medical devices or for sterile injectables. It's irrelevant. Bugs are going to try to grow, if they can, in a water system unless conditions are continuously hostile and keep them from doing so. So everything I talked about is completely applicable to medical devices, because the water systems that are designed for medical devices, device manufacturers, are identical in the nature of the water systems designed for just about any non-sterile manufacturing operation. Okay, let's see what happened to my chat. It just went away. I've got another one here. What are some of the hot water sanitizable RO and or UF vendors? That's a good question. I know that they're actually widely available. The company used to be US Filter, now is Siemens. I know they provide hot water sanitizable systems. Actually, just about anybody who designs and installs pharmaceutical water systems will be getting, if they don't make the equipment themselves, they will get it from vendors that do make hot water sanitizable systems. So they're actually widely available now. In fact, most systems that are being put in to this day have hot water sanitizable systems that are being put in. You know, there's still some cold systems or some ambient systems that are being put in because not everybody has available, you know, heat sources in order to be able to heat a system like that. But it's very typical for just about any vendor who could put in a water system to be able to put in a hot water sanitizable system. Another question here is there a typical frequency for hot water sanitization of membrane systems? That's a good question. I have seen everything from daily to weekly. I've not seen as infrequent as monthly, and I think that would be a mistake to go as infrequently as monthly. But certainly daily and weekly are very typical. If it was daily, you would actually prevent any chance of biofilm development, and so you wouldn't. Remember, hot water sanitization does not clean the dead biofilm away; it just kills it. And so if you leave all this debris behind, that's dead debris, it winds up being food for that further, development of biofilm, and so or a more rapid development of biofilm then. I'd say that you're probably better off doing it more frequently than less frequently. And remember that even if you do hot water sanitize the system on whatever frequency, that does not eliminate the need to do a chemical cleaning, because you will still need to clean away some of the inorganic deposits, the scales, and certainly some of the accumulated organic debris, because it's not all biofilm that accumulates. Sometimes it's just organic molecules that impinge on the surface and biofoul the surface with an organic residue that's not living. And so you still have to clean the systems on a periodic basis, but I think that you're going to find the cleaning less necessary if you sanitize more frequently rather than less frequently. But again, daily to weekly is pretty typical. I don't see any more questions showing up. Do we have any other questions by chat, or maybe you can open up the lines, Sam, and maybe we can get some verbal questions in.
Thank you, Terry. Meanwhile, we sincerely request you to share your feedback in the feedback form that will appear on your screen in the polling panel right now. The feedback form has just 6 questions, mostly multiple choice in nature, and it wouldn't take more than 2 minutes of time to answer. The polling will remain open till the end of session, and you can answer it even after Q&A is over. We would be grateful if you could stay back a little longer and complete this feedback for us. Terry, we have questions coming up here.
Okay,
I just sent you.
I see it.
We have a couple of other questions as well.
Okay.
I'll send it to you.
I'll read this one that I got right now. It says, what chemical sanitants could be used in water systems? For example, chlorine dioxide. This is a question for process piping as well. It's a good question. I could talk literally for an hour and a half on this subject because I have a webinar on this very thing. Chlorine dioxide is one of the choices that could be used. Its claim to fame is that it actually can, as a gas, penetrate biofilm and kill the organisms down deep within biofilms. The problem with any kind of chemical sanitant is that penetration into where the biofilm resides is usually a difficulty. Biofilm is going to grow in cracks and crevices in between elastomeric seals and hard pipe fittings. Biofilm can grow down in these places, and no matter how aggressive the chemical is, it will just not penetrate down into these cracks and crevices. And so if you're having any kind of chemical sanitizer that you're trying to use, they are all impeded in their ability to penetrate into these difficult to get to places, these cracks and crevices, we'll just call it. Usually chlorine dioxide is not my first choice. My first choice for a routine sanitant would probably be something like MinCare, this combination of hydrogen peroxide and peracetic acid. That's very effective, even at fairly dilute concentrations. Probably my next choice down would be hydrogen peroxide by itself, but it's not as effective, believe it or not, as the combination at a more dilute concentration even when you have the combo product like Spore Cleanse or MinCare. Going down from that, my third choice, peracetic acid and hydrogen peroxide alone, individually, were about neck and neck, and even second place. Third place would probably be something like hypochlorite. The problem with hypochlorite is that the alkaline pH that it typically exists at is where the hypochlorous acid molecule, which is the business end of the chlorine, is the least effective. And so if you were to acidify the hypochlorite treatment concentration that's in the hundreds of ppm level, it would be much more effective. Most people don't do that or don't think to do that, and there are some issues with chlorine gas evolving from that if you acidify too much. So there are some issues associated with acidifying hypochlorite or bleach. But it is cheap, and you can use it tons and tons, and it doesn't put you in the poorhouse, unlike some of the other proprietary sanitizers. If you ever get a system that is out of control and you need to nuke it in some fashion in order to get back into control, chances are neither chlorine dioxide nor MinCare are going to do it for you. You're probably going to have to go in with a chemical cleaner, perhaps like caustic. 1/10 or 1% caustic would be a good thing to use. I do not recommend using mixture ingredients like, for instance, CIP 100 or something that is a caustic, because it also has a surfactant in it, and if you get a surfactant into your water system, it may be very, very difficult to get it completely rinsed out and pass your TOC afterwards. But at any rate, caustic can be a good nuking agent to get ahead of the problem and then go back to something that's a little bit more reasonable to use if you're in chemical sanitization. If my strong preference for anything is going to be heat. If you can do it with heat, that's your best choice. Because, like I mentioned, it doesn't take much heat to kill organisms, and it does penetrate, although it does not remove the dead biofilm. And the second choice after heat, before you get to the other chemical sanitizers, would be ozone, because ozone can pretty much be used continuously. So that's sort of the in a nutshell, my opinion on sanitizers. Looks like we got another question here. What techniques or procedures are needed to remove biofilm? Well, we sort of dealt with that. If you use an oxidizing sanitizer, it will oxidize away the slime slowly, and if you give it enough time and a high enough concentration and good shear action, don't soak, but rapidly circulate the water, you will shear away and degrade the biofilm. So make sure circulation is part of your sanitization scheme. The more aggressive the oxidizing potential, the more effective will be the eating away process. Ozone is probably the highest. and sodium hypochlorite probably the lowest, and there's probably 1,000-fold difference between the two. And somewhere in the middle is your min-cares and your hydrogen peroxides and all that stuff. Ironically, chlorine dioxide is sort of at the end of the boat, at the low end of the scale, but that's its advantage from the standpoint of killing cells inside a biofilm. But for removing biofilm, forget it, not very good. There is a proprietary cleaner out there now that is designed to kill and remove biofilm. It's been recently approved by EPA for removal of biofilm. It's made by Sterilex, S-T-E-R-I-L-E-X, and let's see, it's got a proprietary trade name called the Perquat technology. It basically uses alkaline hydrogen peroxide combined with a quaternary ammonia compound and a chelating agent. And that combination of those ingredients, given rapid circulation and sufficient contact time, will supposedly, according to EPA, and they don't just approve this for anybody. In fact, this is the only chemical that's been approved for biofilm removal. The compound's called, or the company name is Sterilex, and it's the Perquat technology, and that's good for removing biofilm. I still like plain old ordinary caustic for removing biofilm. It dissolves the actual matrix, the polysaccharide slime matrix, the exopolymer, and once you've dissolved, destabilized that, the biofilm goes with it. Of course, the alkalinity will kill the cells once it penetrates down to them. But again, strong circulation with either the Sterilex product or the caustic is a good way of getting rid of existing biofilm if you have a lot of it. If you have lots of cracks and crevices in your system and you cannot use heat, then you are probably going to have to disassemble some things in order to hand sanitize some pieces and parts that it would otherwise never get to. So there's some issues associated with removing biofilm that are very challenging because it can get everywhere, especially if you've given it enough chance to get everywhere by not sanitizing very often. Do we have any more coming in, Sam?
Thank you, Terry. So as of now, I do not see any other question coming up here.
Okay.
Meanwhile, I would like to inform about the past webinars of Dr. Terry C. Solly. On the screen, you can see a list of webinars, which is available in the form of recorded version. And if you'd like to register or purchase any of these webinars, you can just log on to www.globalcompliancepanel.com and you can purchase these webinars. Also, we have upcoming webinar of Terry C. Solly on 12th of March 2013, Tuesday, on the following topic, which you can see on the screen. If you'd like to register to take part in this webinar, please log on to our website or follow the link on the screen for more information of Terry C. Solly's webinar. Terry, before we end the session, do you have any concluding remarks?
Other than I can tell you that the world of pharmaceutical water systems, which obviously applies to the medical device world as well, the world of pharmaceutical water systems is full of all kinds of things to learn about how they work and how to control them. I try to present webinars that give you little helpful hints on how to do some of these things that you're involved in doing, because I do understand how these water systems do work. I appreciate your attendance today, and I appreciate the good questions that have come, because trust me that we don't always get good questions like we got this time. I hope I was able to answer them satisfactorily to the questioner's satisfaction there. But at any rate, I thank you again for participating today. I've enjoyed this. And maybe I'll see your name listed in the participant list in the future in future webinars. Thank you again.
Thank you very much, Terry. We are grateful to all of you for taking part in this webinar. If you'd like to get in touch with us, you can send us an email to webinars@globalcompliancepanel.com. If any one of you feel that your team members or colleagues or friends might benefit from this webinar, we are happy to inform you that this webinar will be available in the recorded format and you can purchase from our website, or you can also call us at 800-447-9407. We welcome your suggestions and feedback or ideas on how we can improve our webinars. If you'd like to suggest a topic or desire a customized corporate training, we ensure that whatever is your training necessity, it will be our priority. We look forward to having you with us again sometime soon. On behalf of our presenter, Dr. Terry C. Solly, and the Global Compliance Panel team, I would like to say thank you for taking part in this webinar, and we wish you a great day ahead. Thank you. And thank you very much, Terry.
You're welcome. Thanks, Sam. See you next time.
You're welcome.
Okay.
Thank you.
Bye-bye.
Bye now.
Hello?
Hello, Terry. Hello, Terry.